Welcome to the module 17 of database management systems. From the last module, we are discussing relational database design. So, this is second in the series of 5 modules which will discuss this. We have already seen basic features of good relational design. We have studied about first normal form, atomic domains, and got introduced to functional dependencies. So, we will develop further on that to see how decompositions into good design can be done by making use of the notion of functional dependencies, and we will more formally introduce the theory of functional dependencies. So, that is all that we discuss in this. So, decomposition using functional dependencies is the first thing that we look at, and the first normal form of relations which was studied we look at is Boyce code normal form. So, normal forms are kind of a set of properties which is satisfied by a relational schema, and if they are satisfied, then we have certain guarantees in terms of what can or cannot happen in that relational schema design. So, Boyce code is a simplest kind of beyond 1 NF is the simplest kind of normal form, and a relational schema is said to be in Boyce code normal form if with respect to a set of functional dependencies, all functional dependencies in the closure. So, in respect of f we compute f plus, which is a closure, and if I have a dependency alpha determines beta, then naturally alpha will have to be a subset of R, beta will have to be a subset of R. But what is important is every functional dependency in the closure set must either be trivial, that is right hand side is a superset of the right hand side is a subset of the left hand side, or the left hand side set alpha must be a super key. So, only those kind of functional dependencies are possible, no other functional dependencies are possible. If that is satisfied by the relational schema R, then it is said to be in the Boyce code normal form. So, you can if we look at inst department schema of the combined relations we saw last time, then we will know that certainly this is not in Boyce code normal form, because this functional dependency holds in this schema, where it is neither a trivial dependency and nor department name is a super key. So, this is not in BCNF. So, if a relational scheme is not in BCNF, then the question naturally is, can I make it into BCNF? So, then that process is a process of decomposition. So, what you do, you divide the set of attributes into 2 or more at sets of attributes. So, here let us say that we have a relational schema which has a non-trivial dependency alpha determines beta, where alpha is not a super key. So, with respect to this functional dependency, the relational schema is not in BCNF. Then we can decompose R by 2 sets. One is alpha union beta, take the union of these 2 attribute sets and remove beta minus alpha from R, take the difference of beta minus alpha and remove that from R. The resulting pair of relations, relational schemas will be in Boyce code normal form with respect to this particular functional dependency. So, let us see an example. So, if alpha is department name, beta is a pair of attribute building and budget, we have department name functionally determines building budget. So, alpha determines beta, and we have already seen that it does not hold, it is not satisfied by the inst department. So, you replace it by taking alpha union beta. So, alpha union beta is this set of relational this relational schema, and you do R minus beta R minus difference of beta minus alpha. Beta minus alpha, naturally if this is beta and alpha, then beta minus alpha is necessarily building budget, because the department does not occur in beta. So, this set is building budget, and if I remove it from R, which means that ID, name, salary and department name are retained, but building and budget gets removed. So, I get another relational schema which has these 4 names and it holds the functional dependency ID determining. So, now if I look into this schema R 1 and this schema R 2, there are different dependencies that hold on R 1, and with respect to that dependency R 1 is in BCNF because department name is the super key, is the key, primary key, and with respect to this dependency R 2 is in BCNF because ID is the key. So, I can see that the original combined relational schema was not in BCNF with respect to this functional dependency, but when I do this decomposition I get 2 schemas which are each in BCNF normal form. So, this is the basic process and we will see depending on the normal form and different notions of functional dependencies, we will see how these conversions can be done, but this is a basic approach of converting a schema into a normal form. Now, the question is if the constraints including the functional dependencies, if we look at, then functional dependencies will have to be checked on different instance. Now, in general it is difficult to check a functional dependency alpha determining beta if the attributes alpha and the attributes of beta or the attributes of beta are distributed between multiple relations, because naturally how do I check if they are true, if how do I check that 2 tuples which match on alpha is indeed matching on beta unless I perform a costly join operation. So, there is the objective is to be able to come to designs where it is sufficient to test only those dependencies on individual relations of the decomposition, and with that I must be able to ensure that all functional dependencies hold. So, it is a very interesting situation. So, we are saying that we will decompose, get into a number of relational schema. Every schema will have a number of dependencies, functional dependencies. So, and those functional dependencies, if they involve only the attributes of that relational schema, they can be tested very easily. And if these functional dependencies together ensure that all functional dependencies hold, that is, if the closure of this set of functional dependencies is same as the closure of the earlier set, the original set, then we say that the decomposition that we have achieved is dependency preserving, because I can actually effectively compute, this is dependency preserving, because I can effectively compute whether every dependency is satisfied by checking on every individual relation. But the unfortunate part of the reality is that it is not always possible to achieve a Boyce code normal form decomposition which also preserves the dependencies. So, if there are, in some cases we will be able to do, like the example we saw just now, the instructor and department, but it is not always possible. So, we usually need another weaker form, normal form, which is known as a third normal form, and we will subsequently look into those. A third normal form is again a relational schema is there, and for all attributes, for all dependencies that belong to the closure of the functional dependencies, this following conditions must hold. Either alpha determines beta is trivial, which is a condition which BCNF had, or alpha is a super key of R, which is also a condition that BCNF had, or each attribute in beta minus alpha, that is right hand side difference the left hand side, is contained in a candidate key for R. It is not very obvious as to why we need that, that will unfold slowly. This is the condition we did not have in BCNF. So, naturally you can see that based on the first two conditions, you can always say that if a relational schema is in BCNF, it necessarily is in 3NF, but not the reference. There could be some schema which is in 3NF because of the third condition, where there exists a functional dependency, so that beta minus alpha is contained in a candidate key for R, but it is not in the BCNF form. And also you can note that the attributes of that are contained in beta minus alpha must be in some candidate key, not necessarily in the same candidate key. If they exist in some candidate key, then itself the 3NF condition will get satisfied. So, if a relation is in BCNF, it is in 3NF, we have already seen that. So, third condition minimally relaxes BCNF to ensure that we have a dependency preservation. We will see this more later. So, I am just introducing the concept of a relaxed normal form here. So, what is the goal of this normalization? Is if to summarize, let R be a relational scheme, F is a set of functional dependencies. We need to decide whether the relational scheme R is in a good form, which means that it should not have unnecessary redundancy, it should be possible to acquire information by doing lossless join. So, in case it is not in good form, we can convert it by decomposition into n relational schema, such that each schema is in good form. The decomposition has a lossless join, so that I can get back the original relation from this, and preferably the decomposition should preserve the dependencies. So, that is what we will target henceforth. So, when we do that, let us quickly evaluate as to we have seen BCNF. So, how good really BCNF is. So, if I have something in BCNF, should I really be very happy always? So, let us look at a relational schema. This is an information relating the ID of a person, the name of the child and the phone number, and naturally the person, the instructor may have more than one phone and may have multiple children. So, this is a possible instance as you can see. So, all of these belong to the same instructor. He has, naturally you can see there are two children, and there are this is here, this is here. So, this is here, this is here. So, there are two different phone numbers. So, naturally you have four possible combinations that you need to look at. So, now there is no non-trivial functional dependency in this relation. So, since there is no non-trivial functional dependency, this relation naturally is in BCNF form, because that is the existence of non-trivial dependency is what makes a schema not conform to the BCNF form. So, there is no such. So, this is in BCNF form, and now if you look at but what did we see? The key thing that we saw, if we just go back, the key thing that we saw that there is ample redundancy of data. The same data is entered multiple times. So, the consequence of that could be insertion anomaly. If we want to add a phone number to the same instructor, then we need to add two tuple, because the instructor also has two children. If the instructor had three children, we will need to add 3, and unless this is maintained always, then we will have difficulty. So, the redundancy consequences anomaly that we are getting into. So, it could be better to decompose this to say that I make this orthogonal, I keep the child information with the ID and I keep the phone number information with the ID separately. So, if I do that, then I can decompose it in this manner, and if I decompose that, this I have just shown that if you are dividing that table in two parts. So, naturally these are not required, neither are these required. So, these are the entries that I get, and you can convince yourself that you can actually do a lossless join to get back the information. So, BCNF not necessarily give you good designs, and we will see later on that there are other normal forms which can be used to improve on the BCNF. Now, let us for formally getting into how do we convert decomposer relation into a third normal form and how do we assess that, we need to understand more of the functional dependencies. So, we will consider now a little bit of formal theory on them and then develop algorithms that can generate lossless joint decomposition into BCNF and 3NF, and we will also create algorithm to test if decomposition preserves the dependency. So, just quickly to recap, we have already introduced the closure set of a functional dependencies. It is all dependencies that are logically implied by it. Now, the question certainly is, how do I, given a set, how do I compute this closure set? So, to do this, we make use of 3 rules known by Armstrong's axiom, named after the person who first observed them. So, the first rule is reflexivity, which says that if beta is a subset of alpha, then alpha determines beta, always alpha functionally determines beta. So, this is basically reflexivity, you can see, is a different way of saying specifying about trivial dependencies. Next comes the important thing, augmentation, which says that if alpha determines beta, then gamma alpha, where gamma is some set of attributes in R, then gamma alpha will functionally determine gamma beta, which is very easy to see, because alpha determines beta means 2 tuples who match on alpha will necessarily match on beta. Now, if that happens, then whatever is gamma, if 2 tuples match on gamma and alpha, then certainly they will match on gamma and beta, because alpha determines beta tells me that they will match on beta, and gamma is the same set of attributes. So, augmentation also is easy. Then we have transitivity, which we earlier saw also. If alpha determines beta and beta determines gamma, then obviously alpha determines gamma. So, these are the foundational rules observed, which can be made use to compute the closure of the set of functional dependencies. Now, these rules, as I say, this is more for understanding the theory better, is these rules are sound as well as complete. Soundness mean that if I use these rules repeatedly in a set of dependencies, then it generates functional dependencies, all of which actually hold. So, it will never generate a functional dependency which is not correct, which will not hold. And the second, it is complete, which means that if I keep on using these rules, then all functional dependencies that can at all hold will eventually get generated. So, that is a very strong result, and that is what leads to the following example. So, where we are trying to compute the functional closure of the set of functional dependencies here. So, there are 6 attributes in the set, there are 6 different functional dependencies, and we identify some members of the closure. For example, we can see that A functionally determines B and B functionally determines H. So, transitivity clearly show that A will functionally determine H, very clear. So, in the closure that must be there. Similarly, we can see that A functionally determines C. Now, if we augment it with G, that is put G on both sides, then AG functionally determines CG, and we know that CG functionally determines I. So, if we combine these two by transitivity, then we can get a new functional dependency which says AG functionally determines I. So, in this manner you can do the next one also, and you can try to infer several other functional dependencies that can be inferred by different applications of the Armstrong's axioms, the 3 rules, in any multiple different ways. So, to get the closure, what we need to do is now very simple, is certainly we will have a repetitive algorithm to get the closure. The first the algorithm will start with the set of functional dependencies that we have. So, the closure must include the given set of functional dependencies. So, f plus must have f. So, let us start with initial value of f plus as f. Then for every functional dependency is f plus, this is what we keep on repeating, look at the outer loop. every functional dependency that we have f plus now, we will apply reflexivity and augmentation and add the resulting functional dependency in f plus. It is possible that the same functional dependency gets generated and added multiple times, does not matter, f plus is a set, it will naturally eliminate duplicates. Then for each pair of functional dependencies, because reflexivity and augmentation applies to one functional dependency only, but transitivity applies to two functional dependencies. So, for every pair of functional dependencies, we check whether they can be combined by transitivity. If they do, then the transitive closure of that, the transitive functional dependency that arise out of that is also added to f plus. And mind you, the more and more functional dependencies you add, there are more and more opportunities to apply the Armstrong's axiom rules, and newer functional dependencies will continue to get added. But eventually you reach a point where f plus does not change any further, and when that is achieved, we know that the closure of the functional dependencies have been obtained, and that is our final set. We can also observe that based on the rules of Armstrong, the Armstrong's axioms, we can also generate lot of derived rules. Some of those are shown here. For example, if alpha determines beta, if alpha determines beta holds, and if alpha determines gamma, that also holds, then alpha determines beta and gamma together. This is called the union set. So, if there are two functional dependencies which have the same left hand side set of attributes, then we can take the union of their right hand side attributes, and that functional dependency will hold. Obviously, it is trivial to prove this. If alpha determines beta gamma, then alpha determines beta holds and alpha determines gamma holds. This is called decomposition. So, kind of the other side of the union, which also is trivial, because alpha determines beta gamma says if two tuples match on alpha, they match on beta as well as gamma attributes. So, obviously, you take the first part, you get alpha determines beta, you take the second part of the observation, you get alpha determines gamma. So, that is a composition rule. The third is interesting, it is called the pseudo transitivity, which says that alpha determines beta if that holds, and gamma beta determines delta if that holds, then alpha gamma will determine delta, which is not difficult to get, because if this holds, then I can augment gamma on both sides, I get beta gamma, and then I have given beta gamma determines delta. So, if I combine these two in terms of transitivity, I get alpha gamma determining delta. So, this is called pseudo transitivity, because here you are adding another attribute in the transitivity. So, oftentimes it becomes easier to make use of these additional rules to quickly get to the closure set. So, given a set of attributes, we also compute the closure of a set of attributes. So, this is the second concept. We have seen how to, given the set of functional dependencies, how to compute the closure of the functional dependencies. Now, we are given a set of attributes, and we want to define the closure of this set of attributes under the set of functional dependencies. And as the closure of functional dependencies f is denoted by f plus, the closure of a set of attributes alpha under f is denoted by alpha plus. So, this set of closure attributes of alpha is a set of attributes that are functionally determined by alpha under f. So, all set of attributes that are functionally determined by alpha under the set of functional dependencies is member of alpha plus. So, the following simple algorithm can compute the closure. Naturally, initially let us say the result is the final closure set. So, initially we can say that result can be initialized with alpha, because certainly the whole of alpha would necessarily belong to alpha plus by the reflexivity condition. Then for each functional dependency beta determining gamma, we check if beta is a subset of the result. If beta is a subset of the current set of attributes that form result, which mean that alpha functionally determines beta. It will have to, because result is the set of all attributes that alpha functionally determines. So, if beta is a subset of the result, then necessarily alpha functionally determines beta. Alpha functionally determines beta is a consequence of this, and we know that this is there, beta functionally determines gamma. So, combined by transitivity, so I know alpha functionally determines gamma. If alpha functionally determines gamma, then it must get into the result, and this is exactly what this statement is saying, that take result and add alpha, add gamma, the set of attributes gamma, to the result. And how long should you do that? Naturally, you will do that as long as over a full iteration of functional dependencies in F, if there is no change to the result, then you know that all future iterations will have no change. So, you reach a fixed point and you declare that the closure of the set of attributes have been obtained. Now, this closure information is very interesting, and we just show an example here based on the same set of attributes and same set of functional dependencies. So, we are trying to find the closure of the set of attributes A g. So, A g plus initially it will be A g. Now, since A functionally determines C, so given that I can say that C will get included in this set. In the same iteration, if I look at A functionally determines B, so B will get included this set. So, after this first iterative loop, I will have the result as A B C G. If A B C G is there and I am looking at the next iteration, then C G functionally determines H. So, H comes into the set, because C G is a subset of that. The I comes into the set, because C G functionally determines I, and at this point it eventually ends. In this case, in this particular example, you can see that all attributes have got included. So, you can see that it immediately gives you another information as a byproduct of the closure, that closure of A g is all attributes, which mean that A g is a key. It has to be a key, because A g functionally determines all attributes now. So, what is the meaning of A g plus being this? So, the meaning of this is A g functionally determines this set of attribute A B C G H I. Right. So, we will see that this closure set has a lot of valuable information in this. So, we can say that A g is a candidate key, and because this of this, and we can also check whether A g is a super key or not. All that we need to do is drop some member from A g, we drop G and check whether A functionally determines R, which means we check whether A plus is equal to R or not. We check, we drop A from A g and check whether G functionally determines R, which means G plus has to be equal to R, and by that we can easily determine whether the set of attributes is a key or not. So, there are several ways the attribute closure can be used, as we have just seen. It helps you determine whether something is a super key. We can check for testing functional dependencies, because if we have to check whether a functional dependency alpha determines beta hold, all that we will have to do is to compute the closure of the set of attributes alpha, that is alpha plus, and check whether beta is a subset of that. If it is, then certainly it holds. If it is not, then it does not hold. So, it is simple and useful test that can be made use of. So, it can also be used in computing the closure of F, that is, for example, for every subset gamma of R, if we find gamma plus, that is a closure of the set of attributes of gamma, and for each subset of gamma plus, we know that there is a functional dependency gamma determining S, which is just the same statement being made in in different forms. And the closure of attributes is a very nice concept, which help you play around in this multiple ways, and we will see subsequently many of the algorithms for normalization, how they make effective use of this closure set. The notion of both closure of functional dependencies and in very practical implementation algorithms, the closure of attributes. So, to summarize this module, we have discussed further issues in the good design in the context of functional dependencies, and in the process we have also extended the theory of functional dependencies, and we will continue this in the next module to get more insight into the algorithms that actually work with the functional dependencies.